Hello and welcome back to Data Analysis and Visualization. I'm Jovita Christie, and in this video, I'm going to introduce you to the basics of classification. So let's begin. With classification algorithms, you take an existing dataset and use what you know about it to generate a predictive model for use in classification of future data points. So just as I explained in my video on basics of clustering, um, in classification, we require labeled dataset. So when you provide such a labeled dataset, this dataset can be used by the algorithm to learn and make future predictions. If your goal is to use your dataset and its known subsets to build a model for predicting the categorization of future data points, then you'll want to use classification algorithms. When implementing supervised classification, you should already know your data's subsets. These subsets are called categories. So if you are trying to predict if a particular message is positive or negative, if that's what you're trying to predict, then you should already know beforehand that the message is positive or negative in your data set. And then you feed this information to the algorithm to learn. And then when you provide any message that you don't know whether it is positive or negative, because maybe it's a long message, then your algorithm will probably successfully classify it. Classification helps you to see how well your data fits into the dataset's predefined categories so that you can then build a predictive model for use in classifying future data points. Now, once again, this is the dataset that we saw earlier in the previous video on clustering, which shows in each country what is the percentage of income of the bottom 10% population, and also what is the percentage of children finishing primary school education. So this is the scatter plot for the same data set. And once again, we are going to find out how classification is performed on the same data set. In some cases, the subset you might identify with a clustering technique to correspond to the continent's category, but in other cases, they don't. For example, look at the one Asian country in the middle of the African data points, that is Bhutan. So let me just see. So when you see, let's just go back and see that data set. So sometimes what happens is you have a clustering technique and you're trying to do that, but while clustering and dividing something, things can fall into a proper category, but sometimes it may not. So you want to divide everything according to maybe continents, but when you are doing a clustering, you are not able to do that. You're not able to divide into continents because it's possible that based on your algorithm, some Asian country like Bhutan ends up somewhere in the middle of African data points. So this is the original data, and if you see that sometimes there could be a country that ends up in some other continent altogether, just because the clustering algorithm does not use any labels. So let's just quickly go back there to the next slide. Now you could use the data in this data set to build a model that would predict the continent category for incoming data points. So what you want to do is, if somebody gives you a data point, you want to predict in which continent that data point is going to fall. But if you introduced a data point for a new country that showed statistics similar to those of Bhutan, then that new country could be categorized as being part of either the Asian continent or the African continent, depending on how you define your model. So that's the thing, it could fall in the Asian or African continent based on the data point and the attributes that those points have. So this is once again the diagram classifying it according to the continent category. Now imagine a situation in which your original data doesn't include Bhutan, and you use the model to predict Bhutan's continent as a new data point. In this scenario, the model would wrongly predict that Bhutan is part of the African continent. This is an example of model overfitting, situations in which a model is so tightly fit to its underlying dataset, as well as the noise or random error inherent in that dataset, that the model performs poorly as a predictor for new data points. So this is an example of overfitting, which is caused when the model is so overly fit, overly tight on its dataset, that when you provide some new data point, it actually ends up predicting the wrong value. To avoid overfitting in your models, you should divide your data into a training set and a test set. A typical ratio is to assign about 80% of the data into the training set and the remaining 20% into a test set. So the 80% is used to actually make your algorithm learn to train your model, and then the 20% is used to test the model, whether it's working properly or not. Build your model with the training set and then use the test set to evaluate the model by pretending that the test set data points are unknown, but they are not, because they are present in your data set and of course they are labeled. You can evaluate the accuracy of your model by comparing the categories assigned to these test set data points by the model to the true categories, because you're already given the correct labels, so you can compare those labels with the labels predicted by the algorithm. Model overgeneralization can also be a problem. Now, what is that? Overgeneralization is the opposite of overfitting. It happens when a data scientist tries to avoid misclassification due to overfitting by making a model extremely general. So this is opposite of overfitting. Overfitting where model sticks to the rules and regulations of the data set, but in overgeneralization, it becomes very general. And when models are too general and end up assigning every category with a low degree of confidence. So they are giving you the category, but they are not really confident about whether or not that category should fall there or not. That percentage of confidence is not there. To illustrate model generalization, consider again the World Bank Income and Education dataset. If the model used the presence of Bhutan to cast doubt on every new data point in its nearby vicinity, then you would end up with a wishy-washy model that treats all nearby points as African, but with a low probability. And this model would be a poor predictive performer, because just because you found this one country, Bhutan, which was wrongly classified to be an African, to be belonging to an African continent, that is why if you decide that now you want to generalize your model a bit, it's possible that because of that, all the nearby points are also brought into Africa instead of being Asian, and that could, but they are brought in there, but with less confidence. The probability is less, the low probability, and that's why your model is no longer reliable. A good metaphor for overfitting and overgeneralization can be illustrated through the well-known phrase, if it walks like a duck and talks like a duck, then it's a duck. So this is a well-known phrase that says, if there's something that walks and talks like a duck, then it's bound to be a duck. And overfitting would completely turn this phrase into something like, it's a duck if and only if it walks and quacks exactly in the ways that I have personally observed a duck to walk and quack. So if you're talking about overfitting, then that's what overfitting would do. And if we're talking about since I've never observed the way an Australian spotted duck walks and quacks, an Australian spotted duck must not really be a duck at all, because because I don't know how that sort of a duck would walk or quack. And in contrast, overgeneralization would say if it moves around on two legs and emits any high-pitched nasal sound, it's a duck. So therefore, Fran Fine, he had a character in the 90s American sitcom The Nanny. So that character must be a duck because moves around on two legs and makes a nasal sound, high-pitched nasal sound. So that is overgeneralization. Supervised machine learning, which is the fancy term for classification, is appropriate in situations where the following characteristics are true. So you know and understand the data you're analyzing, which is the same as clustering. The subsets or categories of your data set are defined ahead of time and aren't determined by the data. So you have already labeled your data. You want to build a model that correlates the data within its predefined categories so that the model can help predict the categorization of future data points. So that is where you would be using classification or supervised machine learning. When performing classification, you need to keep the following points in mind. Model predictions are only as good as the model's underlying data. In the World Bank data example, it could be the case that if other factors such as its life expectancy or energy use per capita were added to the model, its predictive strength might actually increase. So if your data is good, if data has a lot of attributes which are relevant, then the prediction also would become good, would become better. So the prediction is as good as the actual data that you provide. Model predictions are only as good as the categorization of the underlying data set. For example, what do you do with countries like Russia that span two continents? Do you distinguish North Africa from sub-Saharan Africa? Or do you lump North America in with Europe because they tend to share similar attributes? Do you consider Central America to be part of North America or South America? So all these decisions are completely left to you. It depends on how you label these things in your data set before providing it to a classification algorithm to learn. Now we're going to see nearest neighbor analysis, which is used for both classification as well as clustering. At its core, the purpose of a nearest neighbor analysis is to search for and locate either a nearest point in space of nearest numerical value, depending on the attribute you use for the basis of comparison. So you want in a nearest neighbor analysis, you want to locate a point which is nearest to the point that you're studying. So it should be nearest, or it should be a nearest numerical value to the point that you're trying to study or compare. So that is what nearest neighbor analysis does. Now, since the nearest neighbor technique is a classification method, you can use it to do things as scientific as deducing the molecular structure of a vital human protein or uncovering key biological evolutionary relationships, and as business driven as designing recommendation engines for e-commerce sites or building predictive models for consumer transactions. The applications are absolutely limitless. And so a nearest neighbor technique, just to give you a gist of that, they can do scientific things like, predicting molecular structure of a protein or something of that sort. Or they could, do something technical like building recommendation engines for e-commerce sites, and all these things can be done by nearest neighbor analysis. A good analogy for the nearest neighbor analysis concept is illustrated in the GPS technology. Imagine that you are in desperate need of a Starbucks iced latte, but you have no idea where the nearest Starbucks is located. So what do? One easy solution is to simply ask your smartphone where the nearest Starbucks is located. So you're just going to type into your smartphone where nearest Starbucks, and or just write Starbucks near me, and it would give you a location. When you do that, your system looks for businesses named Starbucks within a reasonable proximity of your current location. So they are going to, the application or the map, mostly Google Map, is going to look, first of all, for all the businesses that are called Starbucks close to the location where you are at right now. And after generating a list of results, the system reports back to you with the address of the Starbucks coffee house closest to your current location. The Starbucks that is your nearest neighbor, in other words. And that's just how your nearest neighbor analysis works in practice. As the term nearest neighbor implies, the primary purpose of a nearest neighbor analysis is to examine your data set and find the data point that's quantitatively most similar to your observation data point. So you already have a data set, and if you want to put a data point into a particular category, then nearest neighbor analysis is just going to analyze that data point and find out where exactly it can fit, what is the nearest or, or closest data point to that particular data point that you are studying. Note that similarity comparisons can be based on any quantitative attribute, whether that be distance, age, income, weight, or anything else that you can describe the data point you're investigating. The simplest comparative attribute which we have is distance, of course, which is why we create scatter plots and try to plot data and find the distance nearest. In the Starbucks analogy, the XYZ coordinates of the Starbucks reported to you by your smartphone are the most similar to the XYZ coordinates of your current location. In other words, its location is closest in actual physical distance. The quantitative attribute being compared here is distance. Your current location is the observation data point, and the reported Starbucks coffee house is the most similar feature. Modern nearest neighbor analysis are almost always performed using computational algorithms. The nearest neighbor algorithm, which is known as a single link algorithm, it merges clusters if the clusters share at least one connective edge, a shared boundary line, or in other words, something in between them. So usually we have to decide how many clusters we want to form if you're doing clustering and you are just dividing your data, and suppose there are 10 clusters and maybe 10 is too much, then you might want to merge two to three clusters together, and this is done by checking if they have some boundary in common or something touching. If there is a boundary or edge common, then such clusters can be merged together. So that's how nearest neighbor analysis works. So it basically begins with, if you have 100 data points, then it basically begins with 100 clusters essentially. And then those 100 clusters are reduced and merged and made into lesser and lesser clusters with each iteration of the algorithm. So that's how it works. And I hope you understood the basics of clustering and classification. And I'll be back with the next video. So I'll see you there, and thank you for watching.